Hello students, in our organic chemistry lesson about Halo Alkanes and Halo Arenes, in last session, right, we have some introduction portions, and after the introductions portions we have to idea about the classifications of Halo Alkanes as well as Halo Arenes. Then after a very common point is called as an nomenclature, general nomenclature or common nomenclature, and IUPAC nomenclature that we have to study it in a very deep manner in standard 11, right? So at presently we are not that much focused on a IUPAC nomenclature sections of Halo Alkanes and Halo Arenes. So now we switch over to the next point. It's the nature of CX bond. The meaning of nature of why this nature of CX bond, which can be displayed or which can be demonstrated in this lesson, because as we know that in the prior lessons of hydrocarbon, all CC and CH bonds are not polar in nature. It means the whole molecule is almost non-polar in nature. But in this case of Halo Alkanes and Halo Arenes, as we know that the nature of CX bond is polar in nature. Why CX bond is polar in nature? Because since the halogen atoms, as we know that halogen atoms are more electronegative than carbon. So the CX bond of alkyl halides, mind well, alkyl halide is polarized. The carbon atom bears a partial positive charge, where the halogen atom bears a partial negative charge. So as we know that halogen is a partially negative in nature and carbon is partially positive in nature, we know that the value of fluorine, okay, fine. So regarding to the Linus Pauling scale, which can be given in 1932 by a Linus Pauling, so the scale about the electronegativity scale. So according to this scale, the value of electronegativity of fluorine is 4, while chlorine is 3, bromine is 2.8 and iodine is 2.5, and we know that the value of carbon is 2.5. So most of the Halo Alkanes compounds, they are polar in nature. Now, since the size of halogen atoms increasing, as we know that as we go down in the group in the periodic table in the halogen family, so CX bond length is increasing, and if the bond length is increasing, it means that the bond distance or the distance is definitely increasing. It means that there is a little bit if the distance is increasing, it means that it's easy to break the bond, so it's required a lower amount of enthalpy, so bond enthalpy is decreasing from CF to Ci. So the data which can be given in our textbook likewise, okay, same, okay, fine. So as you know, the data is like that, okay. So the carbon halogen bond lengths, bond enthalpy, and one more point is dipole moment. So we know that CH3F, CH3Cl, CH3Br, CH3I. The bond length in picometer, or okay, fine. If we convert into angstrom, so definitely you have 1.39, 1.78, 1.93, and 2.14. So as you know that from fluorine to chlorine to bromine to iodine, the size of halogen is increasing. It means that the bond length is increasing. So bond length and bond enthalpy, they are inversely proportional. So 139, so 452 kilojoule per mole energy is required to break the CX bond, 351, 293 and 234. But one more data is about the dipole moment. So there is an interesting case that we have to observe in the case of dipole moment, because as we know that if the electronegativity is decreasing, it means that the dipole moment is decreasing. But mind well, in this case CH3F and CH3Cl, so CH3Cl compared to the CH3F is having a greater value, but now then the order is decreasing. So why this case that we have to observe, or why these exceptions that we have to observe? So in our NCERT textbook, they do not display or they cannot explain this type of the concept, but we explain in such a manner that as we move from fluorine to iodine, As we know that the electronegativity of halogen atom is decreasing, therefore the polarity of CX bond and hence the dipole moment of haloalkane should be decreased accordingly. But the dipole moment of CH3F is slightly lower than that of CH3Cl. What is the reason behind that? The reason behind that, the magnitude of negative charge on fluorine atom is much higher than that on the chlorine atom. But due to small size of fluorine as compared to the chlorine, the CF bond distance is so small, so the product, so dot product of the charge and distance, because what is the formula of mu is equal to charge and distance? So the product is small. That's why CF having a lower amount of dipole moment compared to the CH3Cl. So this is all about the nature of CX bond. So in nutshell, it's a polar in nature. If we move from upward to downwards, bond length is increasing, bond enthalpy is decreasing, and next point is about the dipole moment, which can be calculated in d by. So CH3F and CH3Cl. So CH3Cl having a higher value. Okay, now our next point, next important point is the methods of the preparations of haloalkanes. It's the most important point because we have to prepare methods for haloalkanes. Okay, methods for haloalkanes. So the first method, it's from alcohols. As we know that there is a method of alcohol. So in our textbook they suggest such a way that so various method to form a haloalkanes from alcohol itself, right? So out of this, because as we know that in the case of alcohol, alkyl halides, these alkyl halides are best prepared from alcohols because which are easily accessible. So the hydroxyl group, this hydroxyl group of an alcohol is replaced by the halogen on the reactions with concentrated halogen acids, sometimes phosphorus trihalide, phosphorus thionyl chloride. So these are the various reagents that we have to use, but first we focus by the actions of halogen acids. So what is in this halogen acid and why we have to firstly use the halogen acid? So in this method, the most convenient method for the preparations of haloalkanes involves the substitutions of this OH of an alcohol by the halogen atom. Okay, so it's a one type of nucleophilic substitutions reactions because there is a substitutions of OH with the help of X. So for a given alcohol, the reactivity of halogen acids in these reactions, the decreasing in order is like that HI, HBr and HCl. It means that hydroiodic acid, as we know that it's a bond enthalpy is decreasing, so they easily produce I minus, right? Same way HBr and HCl. So it's a descending order. What about the order of alcohol? The order of alcohol is a tertiary, secondary and primary because these reactions is the mechanism of this reaction is gone through from a carbocation. So it's a normal process is like that when ROH when reacts with H plus, as we know that this H plus is electrophile in nature, and this electrophile firstly attach with this the lone pair of oxygen. So we get a product is like that because H plus oxygen lose their electron pair, so they lose one electron. So plus charge on oxygen, as we know that oxygen is more electronegative, so definitely they pull the electron of this bonded electron pair between R and O. So now it's converted into R plus, so it's a carbocation, and this R plus is reacted with the X minus, so we get a product Rx plus H2O, right? As we know that the tertiary carbocation, once again, the reaction is a simple example of a nucleophilic substitutions reactions in which the nucleophile means X minus, is attacked to the protonated alcohol molecule with the expulsions of a water, because water is a very good leaving group too. So the nucleophilicity of the halide ions is I minus, Br minus and Cl minus. So the order of the reactivity of halogen acid decrease in the same order, likewise HI, HBr and HCl. as we know that the stability of carbocation decrease in the order of tertiary, secondary and primary. So the order of the reactivity of alcohol is also decreasing in the same order. Fine. We know that the primary and secondary chloroalkanes, now we specially focused on the chloroalkanes, are prepared by passing hydrochloric acid gas through a suitable alcohol in presence of anhydrous ZnCl2. This particularly process is sometimes called as a Gru's process, and in our future particularly explanations which can be this test is given in the form of Lucas test 2, because in the case of chemical properties of alcohol, at that time we have to study this portion in a different way by the meanings of a Lucas test. So what is the role of ZnCl2 in these reactions? Because ZnCl2 is a catalyst that we have to use. The role of the ZnCl2, once again, some students ask the question, why we have to use a ZnCl2 or anhydrous ZnCl2 that we have to use? Because the purpose of ZnCl2 is to help into the cleavage of CO bond, this CO bond, right? Because ZnCl2 is a Lewis acid, okay? So it coordinates with the oxygen atoms to alcohols. So as a result, CO bond is weakens and ultimately breaks to form a carbocation. And these carbocations then readily reacts with a chloride ion to form a chloroalkane. So in the case of tertiary alcohol, because in the case of tertiary alcohol that reacts very readily with a concentrated hydrochloric acid even in the absence of zinc chloride. So zinc chloride is not particularly used for in the case of tertiary alcohol. Now we want to prepare a bromo alkanes. Okay, same way when in the case of chloroalkanes, now we move to the bromo alkanes. So bromo alkanes are obtained by a refluxing. Students ask the questions, what is the meaning of refluxing? Refluxing is the process of heating a liquid in a flask with condenser so that the vapors are condensed back into the flask is called as a refluxing process. With a suitable alcohol with constant boiling hydrobromic acid, this 48% of HBr is used, 48%, right? In presence of a little amount of concentrated H2SO4 as a catalyst. So simple ethanol, mind well, it's a primary alcohol, mind well, okay? In presence of HBr, so there is a removal of OH and substituted with a bromine, so we get a product CH3CH2Br and H2O is removed. So sometimes this HBr, okay, can also be generated during the reactions, means in situation. So if we take a KBr and H2SO4, the first this KBr and H2SO4 they reacts with each other and they form a hydrobromic acid, and now this hydrobromic acid it reacts with ethanol and we give the ethyl bromide as a product. Same way, iodoalkanes are prepared by refluxing a suitable alcohol with a constant boiling hydroiodic acid. 57% of this HI is required. In other way, once again CH3CH2OH HI reflux. Mind well, here there is no presence of H2SO4 or anhydrous ZnCl2. It's a simple reactions, so it's a replacement of hydroxyl group with iodine, so we get a product CH3CH2I and water is related, right? HI may be generated in situation by the excess of this phosphoric acid, 95% of H3PO4 when reacts with Ki, it gives a HI plus KH2PO4. So in situation reactions too. So this is the method to prepare haloalkanes from alcohols. Now number 2 method is the by actions of phosphorus halides. We want to prepare haloalkanes from alcohol with another reagent, and this reagent name is called as an phosphorus halides. So phosphorus halides reacts with alcohol to form alkyl halides in excellent yields, more than 80% or above yield. So out of these methods, mostly this method is used in a laboratory or industrial purpose. So we have to take a ROH, means alcohol. in presence of PCl5, so chloroalkanes or alkyl chloride are prepared by the exchange of either phosphorus pentachloride or phosphorus trichloride on a suitable alcohol. So when we react our ROH in presence of PCl5, we get a product RCl plus POCl3. The name of this compound is phosphorus oxychloride and hydrochloric acid. Same way when reacts with the ROH in presence of PCl3, right? So the simply it's a substitution reactions OH Cl, so RCl and remaining H3PO3 means phosphorus acid is removed. So since same way PCl5 and PCl3, we have to take a PBr3 and PI3, but they are not a very stable compounds. So they are generally in situation by the exchange of red phosphorus on Br2 and I2 respectively. So we have to take a red phosphorus in presence of Br2, it gives PBr3, and this PBr3 is connected with alcohol and we get a RBr. Same way phosphorus when reacts with iodine firstly give the phosphorus triiodide, and this phosphorus triiodide reacts with the alcohol and we get a product is Ri. So in situations reactions with the help of this phosphorus halide. In the title of phosphorus halide, we have to use two different types of phosphorus halide. One is phosphorus trihalide and remaining is phosphorus pentahalide. Okay. Now next method is by the exchange of thionyl chloride. The meaning of thionyl chloride means in presence of SOCl2. In presence of SOCl2. Simple method. First we have to take a ROH in presence of SOCl2 thionyl chloride, in presence of organic base like pyridine. So in presence of a basic media pyridine, we get a product is ROH, means is a substitution reactions of hydroxyl with chlorine. So we get a RCl, and SO2 and HCl they are removed. What is the unique of this method, or what's the best portions in this method? So thionyl chloride, out of this method, thionyl chloride is preferred to hydrogen chloride or phosphorus pentachloride or phosphorus trichloride methods for the preparations of chloroalkanes, because in these reactions both this product SO2 and HCl they are gaseous in nature, right? So they escape leaving behind the chloroalkanes in almost pure form. So there is no process of crystallizations or purification process is not required in these reactions too. That's why this reaction is mostly used compared to the above process. In future, this reaction is also sometimes called as a Darson process too. It's called as a Darson process too. So this Darson process to form a haloalkane from alcohol. So this is all about the first method. In next method, we have to prepare haloalkanes from hydrocarbons like alkane compounds. Okay, but in next lecture.